Sample number 4. Find the outward flux of F given by xy squared plus x squared y plus 1/3 z cubed in the direction of k through the surface of the solid given by x squared plus y squared plus z squared equals 9, which is a sphere center at the origin of a radius 9. Alright, so this is what we're going to do. And in this case, it's the whole sphere, alright? They're not telling us it's bounded below by the xy plane or the usual z equals to 0. And they're not telling us anything, so that means the whole sphere. So we're going to evaluate. We're going to evaluate the double integral. The double integral for surface, the surface integral. Well, actually not. Instead of evaluating the double integral, the surface integral, which will be a pretty big thing, instead we will evaluate the triple integral over Q of nabla dotted with F dV over the volume dV. Well, in this case we need to find the divergence of the vector field, alright? So number 1, the divergence of the vector field, which in this case is nabla dot with F, that is, well, the partial derivative of the first component with respect x, which is y squared, plus the partial derivative of the second component with respect y, that's an x squared, and the partial derivative of the z component with respect z, that's simply z squared, all right? And well, you might want to rewrite it as in alphabetic order: x squared plus y squared equals to plus z squared. And careful, because don't get confused with the divergence, because it looks exactly the same as the equation of the surface that we're dealing with. And no, it's just a coincidence. This is actually this quantity right here, it's going to go here actually. That's the integrand in our triple integral. So this means triple integral of the divergence, which is x squared plus y squared plus z squared dv. And well, so this is where we're going to iterate the triple integral. And well, so we have a sphere, right? So how about we use spherical coordinates in this case, right? We're going to use spherical coordinates, and well, recall that number 1, dv in spherical coordinate is given by rho squared sine phi d rho d phi d theta. All right, and we will also replace x squared plus y squared plus z squared. What is that going to be replaced with in spherical coordinates? Rho squared. So let's go about it, all right? So that's over Q. So let's write the limits of integration. Well, in this case, that's going to be rho squared times rho squared sine phi d rho d phi d theta. Well, so let's look at the first limit of integration. That's for rho. Well, in this case we have a sphere, and what's the radius of the sphere? 3, so that varies between 0 and 3. Now, d phi, okay, careful. Phi, again, is the angle that is formed when, for example, when we walk from the North Pole towards the South Pole. That is, imagine a camera in the core of the planet actually being panned from the North Pole to the South Pole. What's the maximum angle in this case? Pi, all right? So that goes from 0 to pi. And the reason this is from 0 to pi is because it's a whole sphere. If it were only the upper hemisphere, it would have been only 0 to pi over 2, all right? And well, theta in this case, well, that's along the equator, if you will, of the sphere. So that's the usual 0 to 2 pi. All right, unless they said something like, oh, the first octant. Well, that would have been phi going from 0 to pi over 2, and and theta going from 0 to pi over 2 also, right? So, and well, this is going to give us 972 pi over 5. That's final answer. And one more example. Okay, the next and last example is about the divergence of a rotational field. Okay, so let's consider the rotational field, which is a vector field of the form A cross with R, where A is just a constant vector and R it's actually a variable vector. And well, let and in this case, well, that constant vector is the vector 1, 2, 3, and the constant vector is just x, y, and z. Okay, so let S be the hemisphere, in this case, well, hemisphere, so only, but we need to be careful, because for the hemisphere z less than or equal to 0 this time, it's the lower hemisphere this time, right? And together with its base in the xy plane, find the net outward flux across S. Well, number one, so let's define the vector. This vector field, this rotation, and you'll see what's going to happen. I'm going to relate this to something from real life, pretty simple. You'll see. Okay. So F, which in this case A, that constant vector crossed with R, which is, well, I, J, K, and that's a 1, 2, 3, X, Y, Z. And well, let's do this determinant, this 3 by 3 determinant, either by, you can use the formula, you can use the trick I showed you about duplicating the first two columns. Well, I'll give you the result of this. This should give us, let's actually, okay, yeah, so that's going to give us 2z minus 3y in the direction of I minus z minus, wait, that's my negative x. So z, that's positive, minus 3x in the direction of j, plus y minus 2x in the direction of k. So from here, well, to find the net outward flux, we need to evaluate this triple integral of the divergence, right? That is, the surface integral, the flux along the flux through the surface, which instead we're going to evaluate it by the triple integral of the divergence. Let's find out what the divergence of this vector field is. Well, so the divergence of F, it's nothing other, well, the partial derivative of the first component with respect to x, but what's that? 0. Plus the partial derivative of the second component with respect to y, which is, and the partial derivative of the z component with respect to z. Oh, come on, it's all 0. The divergence equals to 0. So we have the triple integral of 0 dv over q. And what's that integral? Okay, how does that make sense? Because we have a rotational field. So what this force is doing is just rotating, which is pretty much the opposite of doing some flux, right? Think of, for example, a chef, for example, when he's preparing a sauce, in a saucepan or something. He adds ingredients, olive oil, garlic, white wine, and then he starts doing this, and all the ingredients start just, circulating. So essentially, a chef's hand is acting like a rotational vector field. And whenever if the chef starts spilling anything of the sauce out of the pan, he's not doing it right. His hand is now a vector that it's doing some divergence in this case, and not everything is going to be the curl in this case, right? So that's how we can relate in this case. So if the chef is doing a good job in this case by not spilling anything, his hand, it's truly a rotational vector field, all right? So there's a theorem for this actually. Pure outward rotational fields of the form F equals A cross R have zero divergence. All right, it's everything circulating, nothing is diverging. Thus, have zero net outward flux, and that's pretty much what it is, right? And well, as a final perspective, just to put everything together, so here is pretty much like a historical of what we did back in throughout the whole calculus course. You know, we first learned about the fundamental theorem of calculus. You know, we integrate all these derivatives. We added all these infinitely many derivatives to come up with the area under the curve. And then we did something similar with the fundamental theorem of line integrals, but in this case we integrated over a path, and pretty much the same thing. And then Green's theorem, circulation form. So we added all these microcirculations, and those microcirculations are circulations over time. That's basically a rate of change. It's basically a derivative. So we added all these infinitely many derivatives into dimensions. Then we turned that into 3 dimensions. So we did this, the circulation for Stokes' theorem and flux for divergence theorem, which is essentially the 3D versions of Green's theorem, right? And well, so no matter how you evaluate or what kind of integration you evaluate, it's all about the same. It's adding infinitely many rates of change, all right? And actually, you know what? This concludes everything.